So 4.1 is inverse functions. So we'll be determining if things are one-to-one. We'll use the horizontal line test, and then also finding inverse functions. So the first problems give us a graph, and they want to know if it's one-to-one or not. So 12, they give us this graph that looks something like this. It's kind of, well, it didn't do a very good job. It's kind of arced. There we go. It's a square root function. So to determine if this is one-to-one, we look at we do the horizontal line test. So when we're determining if something's a function, remember we do the vertical line test where it goes across this way. But if it's a horizontal line test, it's like up and down. So as long as it intersects at only one point, which this one does, then it is one-to-one. So this one is one-to-one. I just typically write it like that. Just kind of shortening it a little bit. 14 is an upside down absolute value function. Whoa. Something like that. So, what do we think about this one? Is this one-to-one or no? No, because it goes through more than once, so I would just say not one-to-one like that. All right, so it's going to look like we're jumping a ton, which we kind of are, but it's just some stuff in the middle that we don't need to worry about as much. And some where they're like telling you to graph the function and then determine if it's one-to-one. I'm like, just use the ones that they've given you. It's easier. You're basically going to do the same thing either way. Anyway, so the next thing says use the definition of inverses to determine whether f and g are inverses. So basically we're going to have an f of x function and a g of x function. We're going to plug them into each other. And if it comes out to be equal to x, they are inverses. If not, then they are not. So 42, f of x is equal to 3x plus 9. G of x equals 1/3 x minus 3. Literally turned that setting off yesterday, and apparently it didn't matter. Turned the whole thing off, and it's still doing it. Okay. All right, so to determine inverses, we do the two composite functions. So the first one's going to be f of g of x, which is going to be anywhere there's an x and f of x, we're putting this function g of x. So this is going to be 3 times this whole piece here. So 1/3 x minus 3, and then plus 9. So the 3's here cancel, so I'm left with x. 3 times negative 3 is negative 9 plus 9. So this comes out to be equal to x. So we're good that way. Always good to check both. One, just in case you had any mathematical mistakes that you can verify, but also two, on a very rare occasion, one direction may work and the other may not as far as them being inverses, so it's always good to check both. So the other way would be g of f of x. So we would be plugging in f of x for x over here. So this is going to be 1/3 times all of this, so 3x plus 9 minus 3. So distributing this, that leaves me with an x. The 9 and the 1/3 give me a 3, and then minus 3 outside, so that gives me x. So that one, these are inverses. So by just showing that they're equal to x, is proving that they're inverses. Like if you want to write, these are inverses, you can, but you don't have to. That is sufficient to show what it's asking based on the instructions. Now, these ones were relatively simple as far as plugging in. Sometimes they don't work out quite as nicely. So if you got one like 46, f of x equals x minus 3 over x plus 4, and g of x equals 4x plus 3 over 1 minus x. I don't know why I just put one random parentheses there. It was weird. So we do the same thing, but these are typically going to take up a lot more space because now there's two x's in here that this stuff has to get plugged into. So basically, I've got to plug in this whole function here and this whole function here, and then I've got to work and get it down. So start out with f of g of x. So I'm going to put this function in for x both times over here. So on top I have 4x plus 3 over 1 minus x minus 3 over on the bottom 4x plus 3 over 1 minus x and then plus 4. So in order to do anything with this, I need to get a common denominator on the top and one on the bottom. It happens that it's going to be the same one, which is nice, obviously, but it doesn't have to be the same one top and bottom. So I'm going to multiply this by the denominator here, so like 1 minus x over 1 minus x. And I'm going to end up doing the same thing on the bottom, so I'm just going to do it all at once so that I can save a step. So on top, I'm going to end up with 4x plus 3, and because these are going to have a common denominator, I'm going to kind of skip one step and write them as one just like individual fraction on top instead of two separate ones and then combining them. So I'm going to have 4x plus 3 minus 3 and then plus 3x all over the common denominator that I got of 1 minus x. And then that's over the denominator piece down here, 4x plus 3 plus 4 minus 4x. And then again, I have a common denominator, so 1 minus x. Now, at this point, I would simplify stuff. If you want to kind of like write some little stuff out to the side to, again, not have to like rewrite. Obviously, you're going to see this takes up a lot of paper. Typically, when I do these, if I do them like fully step by step, it takes at least a half sheet of paper, if not more. So, but what I would do is go through and say like, okay, on top, this 3 and negative 3 cancel each other. Down here on the bottom, the 4x and the negative 4x cancel. If you want to even go as far as to go ahead and say, okay, on top I'm left with 7x, and down here I'm left with 7, like you can do that if you want to simplify it just to make your life a little bit easier as far as like the rewriting step. So now when I have a fraction divided by another fraction, what do I normally do? Or when we say I have, like, I'm dividing by a fraction, what is that the same thing as? By what? Yep, multiplying by the reciprocal. So I'm going to have the top fraction as it is, so 7x over 1 minus x, times, I take this bottom one and I flip it, so it's going to be 1 minus x over 7. So see, that's the nice part. I would have had to like rewrite it if I didn't like do this stuff out to the side, or like, I mean, I know you can kind of do some of this in your head. If it was a little crazier, you might not be able to. So now, since I'm multiplying, I can cancel top and bottom. 7s also cancel, so I'm left with an x. So these are inverses, but that's only one direction. Now, I'm going to tell you, a lot of times one direction's going to look a little crazier than the other. I don't really know why that ends up happening. It's really nice when there's only one x, even when you're dealing with fractions. This one, both obviously have 2. So going back and doing g of f of x, I have 4 times this whole piece, so x minus 3 over x plus 4, plus 3 over 1 minus, and then in parentheses, x minus 3 over x plus 4. So it won't change anything as far as the common denominator, but we just need to remember that this one's a little different from over here, and that we have a 4 that needs to be multiplied up here as well once we deal with the common denominator piece. So common denominator in this case is going to be x plus 4. Again, top and bottom it happens to be. So x plus 4 is what's getting multiplied by these individual numbers. So then I'm going to have 4 times x and 4 times negative 3, so 4x minus 12, and then plus 3x plus 12 over the common denominator of x plus 4. All over on the bottom, this is just 1 times this, so this is just going to be x plus 4, and then minus x plus 3 over the common denominator of x plus 4. So once I get to this point, just like I did on the previous one, I would cancel things. So the negative 12 and the positive 12, and the x and the negative x. I'm left with 7x here, 7 here. I've got 2 fractions being divided by each other, so we're going to keep change flip. So I've got 7x over x plus 4 times, I'm going to flip this one, so this is going to be x plus 4 over 7. X plus 4's cancel, 7's cancel, so I'm left with an x. So again, I have verified that these are inverses. Any questions about that? So this will kind of be, this is why we did composite functions in chapter 3, so that now you can actually use them in an application form. When we do actually finding inverses in just a minute, you can confirm then that you did it correctly by using this method. So that's also why we do this first in this section. And then we go down and actually find inverses. So that way you can check your work if you want to. So we may do that on a couple of them. We'll see. All right. So actually finding inverses now. And it also wants you to graph these functions and find the domain. We're not doing that. We're just skipping that part, and we're doing just finding the inverses. There's other things that we need to get to that are more important than that. So just be aware of that. So 60 f of x equals 4x minus 5. So they're typically going to write it in function form as f of x. If you want to think about it as y, that's fine. And I say that because typically my little catchphrase that I say when finding inverses is swap x and y, solve for y. So I'm going to, let me back up. The reason I say you may want to think about f of x as y is some people really struggle with the fact the f of x represents y. And when I say swap x and y, then they get super confused because they'll come up to me and they'll be like, there's no y in this problem. And I'm like, well, I know f of x is y. So if you want to rewrite this as y, you can. I don't care. However you need to do it. I can just visualize it without it. But I know that can be confusing when you don't directly see it. So just be aware of that. So the first thing we do is swap x and y. So that means wherever y is, I put x. Wherever x is, I put y. And if there's multiple x's, we have multiple y's in the problem. We'll have that in a minute. We don't have that one in this one. But so I'm going to have x equals 4y minus 5. So that's the first thing. Then I've got to get y by itself. So I'm going to add the 5 over. So x plus 5 equals 4y. Then I'm going to divide by 4. So x plus 5 over 4 equals y. And so that would be my inverse, which sometimes you'll see them write that as f to the negative 1 of x. Instead, if you leave it as y, that's fine. I think in the back of the book, if you're looking at answers, it's probably going to say f to the negative 1, which is f inverse, is equal to that. But that's just purely notation. I'm good with whichever way you do it. I will pretty much always do it the way I have it boxed, just because of habit. So at this point, I'm not going to with this one, but I could go through and I could plug this in for x here and show that they're inverses, and I could do it vice versa as well if I wanted to confirm it. So good way to check your work and not get something wrong. And even if you do get it wrong and you're like, hey, I can't figure out where I went wrong, but I know my answer's not right, at least you showed that you put in the effort to check it. So all right, 64. F of x equals negative x cubed minus 2. While I'm thinking about it, Cash, do you have to go early for chapel today? Okay. All right, so swap x and y first. So x equals negative y cubed minus 2. So now I need to get y by itself. I'm going to add the 2. So x plus 2 equals negative y cubed. Divide by the negative now. So I'm going to have negative x minus 2 equals y cubed. Then to undo that, I need to take the cube root of both sides, which will give me the cube root of negative x minus 2. Negatives are okay in a cube root. They're just not okay in a square root, so just make sure you keep that in mind. That ends up giving you an I. Cube roots, negative 3 cubed is just negative 27, so we can take the cube root of that and it's fine. Any even power can't have negative inside. That's the only thing. Now, if it was x minus 2, that's different because x can be different things, but anyways, nothing crazy about this one. So the cube root of negative x minus 2 equals y, and that is fine like that. Is it going to make the box? Okay. Let's see, 70. F of x equals 1 over x plus 2, and they also tell us that x is not equal to negative 2. Why?
Because you can't have 0 on the bottom.
Yep, can't have 0 on the bottom. That would be where a vertical asymptote is. So just throw it back a little bit before Christmas. So that's why they put that caveat on there. That's basically saying domain is everything but this, so any other number is fine, which is part of why in this section they will tell you to state the domain of your new function. So when we do this one, if it comes out to be a fraction, we'll briefly talk about it, of just what x can't be if it is in the bottom, but we'll just see what happens when we get there. All right, so swap x and y. So I've got x equals 1 over y plus 2. So when we start getting to these kind is where I tend to find people have the most issues with finding inverses with these, and then the ones that are like this, when you're like given this and you have to find its inverse, those tend to be the ones that people struggle with the most. So to get y by itself, what I'm going to have to do is I'm going to have to multiply both sides by this denominator. So I'm going to have to multiply by y plus 2 on both sides. So that's going to give me, when I distribute it, x times y plus 2x equals 1. And then now from there, I have something that I'm a little bit more familiar with working with. So subtract the 2x. So xy equals negative 2x. Oh, plus 1. And then I'm going to divide by x. So some people will do this, negative 2x plus 1 over x, which is totally fine. Or the other way that we can do this is y equals, and we can do this as negative 2x over x or plus 1 over x, and then reduce it to y equals negative 2 plus 1 over x. Either of these like answers here is fine. They are both the same thing. It's just two different ways to write it. I would go back and forth personally on which way I would write it. It would kind of just depend on how I'm feeling that day, being honest. Now, what value can x not be here?
-2.
Let me rephrase. In this problem. Just 1 second.
0.
Yes, it cannot be 0. So x can be anything but 0. Yes, ma'am.
Did you, I haven't had a chance to even look at attendance, did you mark Claire got that out today?
Yes.
Okay, she was in the office the whole time, I'm just letting you know, because she was trying to get in the front doors, not realizing her key card doesn't work for that one. And I don't think that kids realize their key cards will never work on the sanctuary doors unless they're in prison. And that's 1 day a week when they come in for practice.
Yeah.
So she stood there for 2 minutes trying to get her sisters in the door when she should have just come around the office and been like, "How's this? Like, we tried, we were here."
Well, I thought it was weird that she wasn't here because usually, like, the kids will know that she's, but I was like, but I had, like, several people that were out.
Today's been a weird day. So
Yeah.
I just wanted to give you a heads up so she was here, but
Okay.
we had such a massive amount of people. Like the end of homeroom was ringing and we saw like 10 people in there.
Yeah.
One of them.
I know. He came in and he was like, Tyson's in the office. I was like, I'll just wait for him.
Mhm.
I was like, it's fine. I was like,
Seventh grader in your class.
huh?
So he's a 7th grader these days.
Nice. Thank you. All right. Let's see. Now, I will also say on this problem, if you didn't write the x not equal to 0, I'm not going to mark it wrong, but that's why they're asking you about the domain, is because they just want to make sure that you're paying attention to the fact that, like, x could not be 0 in this function. So, let's see. 72. So this is going to be one where we have a fraction where there's an x on top and bottom. So f of x equals x plus 2 over x minus 1. X is not equal to 1. So when we swap x and y, every single place there's an x has to have a y. So this is going to end up being x equals y plus 2 over y minus 1. Okay, and again, they've put on that, the little caveat over there, x can't be 1 in the initial function. When we get to the end of our inverse function, it may or may not be 1. Could still be 1, doesn't have to be, just depends. So what I'm going to do is the first step of this one is going to look just like the first step I did of this one. So I'm going to multiply by the denominator on both sides to get rid of the fraction. So I'm going to end up, when I do that, with x times y minus x equals y plus 2. Now, I'm obviously trying to get y by itself, but I see two y's in there. Well, I can't get them both by themselves individually. It's not going to work. So what I need to do is get all the y's on one side, everything that doesn't have a y on the other side. So I'm going to subtract this y over and add this x over. So I'm going to have xy minus this y equals, add this x over, x plus 2. Now, this is the step that I find that people tend to struggle with a lot. What do you think I might need to do now at this point that I have a y in both of those pieces? But they're not just by themselves. How about if I gave you something like that? How could you rewrite that? Ignore this.
X plus 2.
Times what?
3.
Yeah, so you take out the 3 and have x plus 2, right? So you notice there was a 3 essentially in both pieces here. What's in both pieces over here? Y. So I can do the exact same thing. So take out a y, and I'm left with x minus 1. People tend to forget if this y is completely by its, like, quote-unquote, completely by itself. They forget to put the 1, so just make sure you don't forget that. So I've got y times x minus 1 equals x plus 2. Then I'm going to divide. So y equals x plus 2 over x minus 1. Now, what do you notice about that?
It's the same equation.
It's the exact same thing. So that can happen, but it may also flag me that, hey, maybe I should check this one. Maybe I should make sure that I did this right, because it does happen sometimes where the inverse and the original can be identical. Doesn't happen super, super often, at least typically in our book. So let's just check this one. 1, extra checking practice. And 2, let's just verify that we did it right. So, and I'm only going to check it one way. So I'm going to plug in x plus 2 over x minus 1 up here. So what I just found up here. So x plus 2 over x minus 1 plus 2 over x plus 2 over x minus 1 minus 1. I'm going to get the common denominator by doing x minus 1 on both of these. So I've got x plus 2 plus 2x minus 2 over x minus 1 all over on the bottom x plus 2 minus x plus 1 over x minus 1. So x and negative x cancel here. 2 and negative 2 cancel here. So I've got a 3x and I've got a 3. So then keep, change, flip. I've got 3x over x minus 1 times x minus 1 over 3. Cancels, cancels. I'm left with x. So it was an inverse. So it happened on this one that the inverse and the original were exactly the same. I don't see that super often, so it's pretty cool that this one did that. Any questions on that? All right, one more, and then we'll be done with this section. 76.
Miss Quinn, can I do that?
Yeah. F of x equals negative, and then the square root of x squared minus 16. X is greater than or equal to 4. So why does x have to be greater than or equal to 4 in this problem? Because if it was like 3, then we would end up with a negative in the radical, and that would be a problem. So just kind of, that's more of a refresher on domain of stuff there. So we do the same thing with this one, even though it's got a radical. So I'm going to have x equals negative in, I keep wanting to say parentheses, in the radical, y squared minus 16. So first thing, I'm going to divide by the negative. So negative x equals the square root of y squared minus 16. To undo the square root, I square both sides. So that's going to mean that I've got, it's important to note, the negative is attached to the x and that whole piece is being squared. That's going to be important because when a negative gets squared, what happens? Yep, it becomes a positive. So this is going to be x squared equals y squared minus 16. And you could have done that all in that one step. I just did it in 2 separate, in case you go back to look and you're like, what did she do? Then I'm going to add the 16 over. So x squared plus 16 equals y squared. And then ultimately I've got to take the square root of both sides. But when I take the square root of both sides, what is my final answer have to have? As far as radical.
Say that again.
So if I am solving an equation and I take the square root of both sides, my final answer has to be what? Or how many answers do I have?
2.
What are they?
Negative, positive.
Yep. The plus and minus of the radical. So this is going to be plus or minus the square root of x squared plus 16. Now, just for, again, a domain review, are there any values that will cause a problem in here?
Yes.
What would they be?
Any negatives. It's any negatives.
But a negative squared is what?
A positive.
A positive. So in this case, because this is plus 16, which is different than the original, there are no values that are going to cause a problem. If it was a minus minus something, then there could be. But since everything will have to be positive, we don't have to worry about that with this one. So this one doesn't have any caveats for what it can't be, basically. Now, when you're checking the radicals, if you were to be plugging them in, it's not going to matter if you do plus or minus, because when you square that whole piece, everything gets positive anyways. So if you were to check this one, you wouldn't need to check the positive and the negative one. Just checking one of them will work. Any questions on any of that? All right, so what I'm going to do, I'm going to go ahead and tell you what your problems are, but I'm going to give you tomorrow to do them as well. 1, to make sure you have plenty of time to do them, and that way if you have questions you can ask. But 2, we also only have 5 more minutes, and I don't like to just give you 5 minutes to do problems. So 13, 15, 17, 43, 45, 59, 69, and 75. And if you feel like either checking or actually finding the inverses are something that you're struggling with once you do those, most any of the odd ones in those 2 little sections of problems would be really good extra practice if you feel like you need something a little extra. So